Get ready to embark on an epic game development journey and recreate the most popular game ever created, Tetris. With just a few hours of your time, you'll be able to create your very own fully functional and engaging Tetris game using Python and Pygame. Join me as I take you step by step through the process, from setting up the game loop to creating the game grid and blocks to implementing movement, collision detection, and scoring. You are going to learn invaluable game development concepts and techniques along the way. And by the end of this tutorial, you'll have a polished and exciting Tetris game that you can proudly share with the world. To make sure you don't miss out on any updates and new tutorials, be sure to subscribe to my channel and hit that like button to show your support. So, what are you waiting for? Let's dive into the world of Tetris game development together. Subscribe now and let's get started. But why build Tetris on your own if tools like ChatGPT can build it for you in seconds? In today's world of constant distractions, shortened attention spans, and easy access to AI tools, it is important to develop the ability to focus on a complex task and see it through to completion. Building a game like Tetris from scratch will challenge you to break down a complex problem into manageable steps, strengthen your problem-solving skills, and improve your ability to concentrate on a project from start to finish. Today, there are so many distractions vying for our attention, from social media notifications to instant messaging, that it can be difficult to concentrate on any one task for extended period of time. Without focus, it is easy to become overwhelmed by the complexity of a project like Tetris and give up before completing it. By practicing focus and building the game from scratch, you can strengthen this vital skill and become better equipped to tackle any challenge that comes your way. Not to mention the satisfaction that comes with creating something entirely from your own ideas and hard work. I promise you, if you complete this tutorial, you are going to feel very happy. Trust me. Also, learning to build a Tetris game using Python and Pygame is a great way to improve your coding skills and expand your knowledge of game development. By following this tutorial, you'll be able to learn the fundamentals of Python programming, such as loops, conditional, functions, and object-oriented programming. You'll also gain experience with Pygame, a powerful library for building 2D games in Python. To fully benefit from this Tetris game tutorial, it is recommended that you have a basic understanding of Python programming. If you are new to Python, consider watching my Python for Absolute Beginners course first, which can be found in the video description or in this card. Additionally, if you are new to game development with Pygame, I suggest starting with our Pong and Snake game tutorials, also linked in the video descriptions, to make the learning process smoother. Don't worry if you are not yet an expert in Python or Pygame. This tutorial will provide valuable insights and help you learn a lot. As Lao Tse once said, the journey of 1,000 miles begins with a single step. So let's take that first step towards creating our own Tetris game and see where this journey takes us. Tetris may seem complex and challenging to develop, but fear not, we will take a divide and conquer approach to make it more manageable. In this tutorial, we will break the development process down into 13 steps, tackling each one individually and building upon what we have accomplished in previous steps. With this approach, you'll be well on your way to creating your own Tetris game in no time. So let's get started and see how we can conquer this challenging project one step at a time. The first step is to install Pygame. Pygame is a Python library used to create games and multimedia applications. In this tutorial, we will be using the Pygame Community Edition, a fork of the original Pygame library that is updated constantly with new features and bug fixes. However, you can also use the standard Pygame library if you prefer, as the code we will be using is exactly the same. To install the Pygame CE library, all we have to do is to open a terminal window and type the following command: pip install pygame-ce. With the Pygame library installed, we can now verify that it is working correctly by running a simple test script. To do this, we create a new folder. We create a new Python file in it and we name it main.py. Now we can open this file with our favorite editor. I'll be using Sublime Text in this tutorial. Inside the file, we have to import Pygame by typing import Pygame. Next, we have to run the program to see if Pygame is installed correctly. In Sublime Text, simply press Ctrl and P to run the program. If you see the message Pygame CE, our installation is working fine and we have successfully completed step number 1. That was easy, wasn't it? We are one step closer to our goal of building a fully functional Tetris game. Let's move on to step number 2. The next step in building our Tetris game is to create a blank screen and set up the game loop. Before we start, it is important to understand the structure of a game. Every game consists of 2 parts: the part where we define our variables and game objects, such as the grid, the blocks, and the user interface, and the game loop, which is responsible for updating the positions of the game objects and checking for collisions. The game loop is like the heartbeat of the game, running repeatedly until the game is closed. In each iteration of the game loop, we will draw the game objects in their new positions and check for collisions, all happening so fast that it appears as a continuous movement. Now let's create a blank screen and the game loop. First of all, we need to initialize Pygame, so we type pygame.init. Then we create a display surface. A display surface is like a blank canvas where we can draw our game objects. We need to specify the width and the height of the display surface. I am going to use a size of 300 by 600 pixels for now. We will change that later. Let's create the display surface. Screen is equal to pygame.display.setMode parentheses and again parentheses 300, 600. This line of code creates a display surface object named screen. The setMode method takes a tuple as an argument. The first value is the width and the second value is the height of the display surface, our canvas. In simpler terms, we just created the game window and to draw on it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10, 10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system in our Tetris game. That's why it is important to understand the differences between these two coordinate systems. Now that we have created the screen, we need to give it a title. We do that by using the setCaption function. Pygame.display.setCaptions parentheses quotes Python Tetris. Next, we create a clock object like this. Clock is equal to pygame.time.clock. Be careful, we need a capital C here. We need this clock object to control the frame rate of the game, how fast the game will run. Don't worry about this line of code now. we will get back to it in a minute. The basic setup of the game is now complete. Let's now work on the game loop. The game loop consists of three parts. Event handling. First, we need to check for any events that occur in the game, such as quitting the game, a key pressed on the keyboard, etc. It is done using the Pygame event handling system. 2. Updating positions. Next, we update the positions of all the game objects, the blocks, based on the events we detected in step number 1. 3. Drawing objects. Finally, we draw all the game objects in their new positions on the screen. This step uses the Pygame graphics functions to render the objects in the display. By following these three steps, we can create a dynamic and interactive game that responds to user inputs and updates its state accordingly. We start the game loop with a while loop like this. While true, colon. The while loop is an essential part of our Tetris game. It runs continuously until we close the game. At each iteration of the loop, we perform three key steps: checking for events, updating positions of game objects, and drawing the game objects in their new positions. It is important to note that before running the game, we need to ensure that the code inside the while loop has been fully written. If we run the code at this point, the while loop will run forever, since we have not defined a way to stop its execution. So in the next step, we'll add the necessary code to stop the while loop. 4. Event in pygame.event.get parenthesis colon. This line of code gets all the events that Pygame recognizes and happened since the last time the while loop ran and puts them in a list. Then we loop through the list of events and check if any of the events is the quit event. The quit event is when we click the close button of the window. If the event is the quit event, we break out of the while loop. If event.type equals pygame.quit in capitals, colon, pygame.quit, and then we have to close the program completely with the command sys.exit. This command is part of the sys module, so we have to import it like this. In the first line of the code, after importing Pygame, we type, sys. That's it. Now we have defined a way to exit the game, but we need a couple more lines of code before running our game for the first time. We have to update the screen with this line of code, pygame.display.update. This line of code takes all the changes we made in the game objects and draws a picture from them. Since we haven't created any game objects yet, this line just draws a black screen. Remember the clock object we created in the beginning? We need to use it now. We have to tell the clock object how fast the game should run. We do that by using the tick method. The tick method takes an integer as an argument, and that integer is the number of frames per second that we want. I am going to use 60 frames per second. Clock, tick, parenthesis, 60. That's it. This means that the while loop and all the code inside it will run 60 times per second. If we didn't set a frame rate, the game would run as fast as the computer can handle, which could lead to inconsistencies in the game speed. By setting the frame rate, we can make sure that the game runs smoothly and at the same speed for all players. Now that the game loop is complete, we can run the game for the first time. If we run the game at this point, we won't see anything inside the game window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the game by clicking on this X icon here. Beautiful. The game window is black. Let's make it a dark blue color. Pygame provides several built-in colors, but we will be defining our own colors for this game. In Pygame, colors are represented as a tuple of 3 values, each value representing the amount of red, green, and blue in the color. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, we will create a tuple with the following values. Red is equal to 255, 0, 0. These values represent the red, green and blue components respectively. So, to create a dark blue color, we will create a tuple like this. Dark blue is equal to, parenthesis, 44, 44, 127. Now, let's paint the game screen dark blue. Inside the game loop, before updating the screen, we will call the fill method of the screen object like this. Screen.fill, parenthesis, dark blue. The fill method just fills the display surface we have created, our canvas, with the color we define, in this case, dark blue. If we run the game now, we can see the game window is now dark blue. Beautiful! We just completed a very basic game loop, so we can remove step number 2 from our list. We have made progress. Now, let's work on step number 3. To prepare for writing code, it's important to take a step back and think through the game logic thoroughly. In Tetris, the gameplay area is a grid consisting of 20 rows and 10 columns. The game pieces, or tetrominos, fall down the grid, and the player must arrange them to form complete rows without any gaps. We will count the rows from the top to the bottom and the columns from the left to the right, with the top left cell at row 0 and column 0 being the origin. To represent the grid, we will use a two-dimensional array, which can be implemented as a list of lists in Python. In our implementation, empty cells will be represented by the value of 0. When a tetromino, a block, is permanently placed on the grid by the player, the corresponding cells will be assigned a value, reflecting its color. For example, if we place a red tetromino on the grid, we will assign the value 2 to the cells it covers. Similarly, if we place a yellow block, we will assign the value 4 to its corresponding cells. Each color has a unique numerical value, and since there are 7 different colors in the game, the values used in the 2D array will range from 0 to 7. 0 for an empty cell and 1 to 7 for the colors of the blocks. So if the game state at some point is something like this, the two-dimensional array will look like this. However, the current block that can still be controlled by the player will not be reflected in the array and will instead be stored and managed separately in the game logic. Now that we have a clear understanding of the game grid, we can begin implementing it in code. Let's go back to our code. We are going to use object-oriented programming to help us organize our code. We will create a grid class. Let's create this class in a separate window. I press Ctrl and N to create a new file, and then Ctrl and S to save it as grid.py. Now we can start writing our grid class. We type class grid : Now let's create the init method, which will initialize the grid object. What do we want to know about the grid? First, we need to know how many rows and how many columns it contains. So let's create 2 attributes to store this information. Def init parenthesis self : self num rows is equal to 20 and self.numCols is equal to 10. Next, we need to know the size of each cell of the grid in pixels. Let's make each cell 30 pixels in width and height. Self.cellSize is equal to 30. Now we need a two-dimensional array to represent the grid itself. As we said, we are going to use a list of lists to represent a two-dimensional array. So let's create that list. Self.grid is equal to brackets and again brackets. Now we have to fill that list of lists with zeros. One way to do is this one. I now have a list of lists that each contains 10 zeros. This is a representation of our grid filled with zeros. But creating the lists like this requires a lot of space in the file, and this is tedious. We programmers don't like to repeat things manually. We like to automate things. We can do the same thing with just a single line of code. Check this out. Self.grid is equal to opening bracket and again an opening bracket, 0 for j in range, self.number of columns, a closing bracket, and then for I in range, self number of rows, and closing bracket. This line is called a list comprehension. It is a shorthand way to create a list of lists or a 2D list. The inner part, this one, creates a list of zeros with length equal to self.number of columns, in our case 10 zeros. This is done self.number rows times because it is wrapped in another list comprehension, which repeats this process for self.num rows times for 20 times. So the resulting list is a 2D list with self.num rows and self.num columns where each cell is initialized to 0. Cool, huh? Let's print this grid at the terminal to see if it works. Let's create a method for it. Def print grid parenthesis self colon for row in range parenthesis self.number of rows colon, and then for column in range parenthesis self.number of columns print parenthesis self.grid brackets row brackets column comma and equals quotes and a space inside the quotes and closing the parentheses, and then again print. This code iterates over every cell in the grid and print out its value row by row, with each row printed on a new line. This method will be useful if we want to see the state of our grid later on. Let's now create a grid object in the main file and print it to see if everything works as expected. I can press Alt+1 and Sublime Text will get me back to the first open tab, our main.py file. Now we have to import the grid class from the grid.py file. From grid, that's the file name, import grid, that's the class name. Now we can create a grid object. We type GameGrid is equal to grid. Now we can call the printGrid method, GameGrid.printGrid. And now let's run the program. Cool, as you can see, at the terminal we can see all the contents of the grid, a 2D array filled with zeros. Our grid is ready. Now let's go back to the grid class to work on it a little more. Alt+2 and Sublime Text get me back to the grid class. What else do we want the grid to know about? The grid must also know the colors to use to display each cell. So let's create a list to hold all the colors it will use. Self.colors is equal to. As we said, we have 7 blocks in the Tetris game and each block has its unique color. So we're going to need 7 colors for the cells of the blocks and 1 color for the empty cell, a dark gray color. Let's create a method that will return a list of 8 colors. Def get cell colors parenthesis colon. Now let's create the colors. As we said, a color is just a tuple of 3 values. So let's create the tuples. Here are all the colors. I have created a tuple for each color and a tuple for the color of the empty cell, this one. Now let's put all of them in a list and return that list. Return dark gray, green, red, orange, yellow, purple, cyan, blue. The order of the list is important. We are going to use the index of each color later on when we draw each cell on the screen. The index corresponds to the block ID, but more on that in a minute. So now in the init method, we can now load the list of colors. Self.colors is equal to self.getCellColors. That's it. The init method of the grid class is ready. Now we are ready to draw the grid. Let's create a draw method. Def draw self colon. We need to draw each cell of the grid with a specific color, with dark gray color if the cell contains a 0, with green color if the cell contains value of 1, and so on. So, first we have to get the value stored in each cell of the grid. We will use a nested for loop for this. For row in range, parenthesis, self.number of rows, colon, for column in range, self.numCols, colon, cell value is equal to self.grid brackets row brackets column. This code iterates through each cell in the grid and assigns the value of that cell to the variable cell value. Now it is time to draw this cell on the screen and give it a color. Now, before we draw something, let's talk about how Pygame draws on the screen. We have three basic concepts to learn: the display surface, the regular surface, and the rect. The display surface is the surface where we see all the game objects. It's like the blank canvas we talked about before. The display surface is created when we call the setMod function, and it's the object we use when we call the update function. A regular surface is a surface like the display surface that we can draw on it. We can have as many surfaces as we want in a game, unlike the display surface, which we can only have one per game. We are going to use surfaces to draw text on the display surface later on. A rect is a rectangular area. It has a position and a size. We use rects for the collision detection, easy manipulation of objects, and for easy drawing on a surface, as we are going to find out in a minute. Now that we know the basics of how drawing works in Pygame, let's draw our first object, a cell of the grid. First of all, we have to create a rect to contain the cell. This rectangle will be invisible, but it will help us draw the cell on the screen. So we type cell rect is equal to pygame.rect parenthesis x, y, w, h. We need to know four things to create the rect object: the x and y coordinate of its top left corner, its width, and its height. The x is going to be column, but since we are using a grid, we have to multiply this by the self.cell size. We do the same thing for the x, row times self.cell size. Now the width is going to be cell size and the height is also going to be cell size. Cool. Now we can draw the cell. We are going to draw it as a square. We are going to call the pygame.draw.rect method. Before using this method, we first need to import the Pygame module. So at the beginning of our grid class, we import Pygame. The pygame.draw.rect method requires three arguments: the surface to draw the object on, a color, and a rect. We have everything we need. The surface we're going to draw on is the display surface we created in the main.py file, named screen. Since we are in the grid class and not in the main.py file, we have to pass the display surface named screen as an argument to the method. So we type screen here. The color is the color stored at the colors list. But which one? We can use the cell value to index into the color list and retrieve the color tuple for that specific cell. So we type self.colors brackets cell value. Since our grid now only contains zeros, the cell value variable will be 0. So this will return the first color of the list, which is a dark gray color. Then we have to tell the draw function that the rect we want to draw is the cell rect. That's it. Our draw method is ready. Let's use it in our code. Let's go back to the main file and call the draw method of the grid object we have created inside the main loop. So after the screen.fill method, we type gamegrid.draw and we pass in the screen display surface. Let's run the program. When we run the game, we see a gray screen because all the cells are the same gray color and there is no visible space between them. To make the cells visible, we need to add a margin of 1 pixel to each cell. Our cell size is 30 by 30 pixels, so we can draw a 29 by 29 pixels gray rectangle for each cell to create the margin. This way, the grid lines will be visible, making the game more understandable and easier to play. Let's do it. In the draw method of the grid class, in the rect method, we need to make some changes. We need to add +1 here and here. This way, we add a 1 pixel offset at the x and y position of the grid rectangle we are drawing. Also, we need to subtract 1 pixel from the width and the height of the rectangle we draw because we said we need it to be 29 pixels. That's it. If we run the game once more, we can see that the grid lines are now visible. Beautiful. Our grid is visible. Now let's modify the values of some cells to see if our grid can display them in different colors. So, outside of the game loop, let's hardcode the values of some cells as a test for our grid class. Let's set some values in the grid. Firstly, we will make the top left cell hold the value 1. GameGrid.grid bracket 0 bracket 0 is equal to 1. I can duplicate this line by pressing Ctrl Shift and D. Next, let's make the cell at the 4th row and the 6th column hold the value 4, and the cell at the 18th row and the 9th column hold the value 7. It is important to note that the counting for the rows and the columns starts from 0, so the 4th row is actually the row with index 3. Let's run the game again to see the changes we made. Great! Now we can see that the cells are displayed with different colors, indicating that the game is functioning as expected. Additionally, we can check the console to see the values of each cell, including the one we have just changed in the code. Perfect! We have just completed step number 3. Congratulations on making it this far in the tutorial. You are doing great. Let's keep going and continue building our Tetris game. The next step is to create the blocks of the game. As you know, Tetris is a game where you have to fit different shapes made out of 4 tiles each. There are 7 types of shapes in total, called tetrominos. When you start the game, the blocks appear in a certain way. The blocks in Tetris can spin around a point, usually in the middle of one of their tiles. For instance, the T-shaped block rotates around the center tile. The I block and the O block in Tetris rotate differently than the other blocks. The I block rotates around a point that isn't in the center of a tile, while the O block doesn't appear to rotate at all. To represent the blocks, we imagine a box around each block that's big enough to fit it in all 4 rotation states. The box is divided into a grid, and we label the top left cell as the origin, row 0, column 0, just like in the game grid. For each of the 4 rotation states, we store which cells are occupied in this grid, not all the cells of the grid. Let's use an example to make this clearer. Imagine the T block in Tetris. We draw a box around it and divide it into a grid with 3 rows and 3 columns, making 9 cells in total. However, we only need to store the cells that the T block occupies, not the whole grid. If the T block is in its first state, state 0, we only need to store the values 0, 1, which means that the cell in row 0 and column 1 is occupied. We also need to store the values 1, 0, 1, 1, and 1, 2 for the other occupied cells. We repeat the same process for the T block's remaining 3 rotation states, storing only the occupied cells for each. This is how we represent all the blocks in Tetris using this same process for each one. Using the bounding grid approach to represent the blocks has a big advantage. It makes rotating the blocks much easier. To rotate a block, all we need to do is to update a state variable that indicates the current rotation state of the block and modify the occupied cells stored in the grid accordingly. This means we don't have to calculate the new positions of each tile in the block, which can be complex and time-consuming. Instead, we simply update the occupied cells in the bounding grid, and the game engine takes care of displaying the blocks in the correct rotated state. Okay, now that we know how to represent each block using the bounding grid approach, let's return to our code and start implementing it. Now, before we start coding, let's leverage an object-oriented feature to simplify our code: inheritance. Inheritance is like passing down traits from parents to children. In Python, it allows us to create a new class that is a modified version of an existing class. The new class, called the child class, will inherit all the attributes and methods of the original class, called the parent class. Then we can add new attributes and methods or override the inherited ones in the child class to customize its behavior. This way, we don't have to repeat the same code for similar classes, and we can make changes to the parent class that will affect all the child classes. It's like having a template that we can reuse and modify without starting from scratch every time. In this game, we have 7 different blocks, but they all share some common properties and behaviors. Instead of creating separate classes for each block and duplicating the same code, we can create a base block class with the shared code and characteristics, and then create 7 new classes for each block that inherit from the base class. This means that each of the new classes will automatically have all the properties and behaviors of the base class without needing to repeat the code. Using inheritance helps us to simplify our code and make it more efficient. Even if you haven't used inheritance before, it's not a problem. It's actually a simple and powerful feature of object-oriented programming. Once you understand how it works in this game, you'll be able to apply it to other projects as well. Let's start by creating the block class, the base class for all the blocks. Let's create a new file and call it block.py. Now we type class block def init parenthesis self . To create a block class, we need to determine what information each block needs to store. The most important thing is to distinguish between different blocks, so each block will have a unique ID. To add this attribute, we can create an ID attribute in the class. Self.id equals ID. We need to pass this ID as an argument in the init method. To represent the cells that the block occupies in a grid for all rotation states, we need to create an attribute called cells. Self.cells is equal to. This attribute will be a dictionary, so we initialize it with an empty set of curly braces. We will use this dictionary to store the occupied cells in the bounding grid for each rotation state of the block. A dictionary in Python is a collection of key-value pairs, where each key is unique and maps to a corresponding value. If you are not familiar with dictionaries in Python, don't worry, I have a detailed video explaining everything you need to know. You can watch it by clicking on this card. Next, we need to know the size of each cell of the block in pixels. Let's make each cell 30 pixels in width and height. Self.cellSize is equal to 30. The next thing we need to know is the rotation state of the block. So let's create a new attribute named rotation state and set it to 0. Self.rotationState is equal to 0. The last thing we need to know for the block for now is the colors it has to use to draw each occupied cell on the screen. The colors are the same ones we used in the grid class earlier, so we can copy the method from the grid class and paste it in the block class. However, this will result in duplicate code, which is not a good programming practice. We want to avoid duplicate code as much as possible to keep our code organized and easy to maintain. So we will create another class to hold all the colors and use it in both the grid and block classes. This class will be called colors and it will have attributes for each color we need in the game. Let's do it. We press Ctrl and N to create a new file and Ctrl and S to save it as colors.py. Let's create the colors class. Class colors : Now, all we have to do is to paste the color definitions. We copy and paste them from the grid class. To make our lives easier, let's create a method for this class that will return a list containing these colors in the specific order we want them. Let's learn something new now. We're going to type the following: add class method. This is a Python decorator that allows you to define a method that can be called on a class rather than on an instance of the class. Now we can create the method we want. Def get cell colors, parenthesis and a colon. We also need to pass in CLS here. This way we can access the attributes of the class. CLS is a reference to the class itself, and it allows us to access the class level attributes and methods. It's similar to using self to access instance level attributes and methods, but CLS is used for the class level. So now all we have to do is to return a list with all the colors we need for the cells, just like we did in the grid class. So let's copy the return statement from the grid class to the color class. We just have to add CLS dot before each color definition to get these colors values. That's it, our color class is ready and we can use it at once. First of all, let's use the color class in the grid class. Let's import it. From colors, import colors with a capital C. Now we don't need the getCellColors method anymore, so we can remove it. In the init method, we just have to call the getCellColors of the colors class like this: colors.getCellColors. Our grid class is ready. Let's go back to the main file and run our program again to see if everything works. Cool! Our game works with the new colors class just like before. Now let's go back to the block class. First, we're going to import the colors class. From colors, import colors. As we said before, we need a colors attribute. Let's create it. Self.colors is equal to colors.getCellColors. That's it. We now have a list of all the colors we need to use to draw a block on the screen. The block class will have a draw method that will be responsible for drawing the block on the screen. Let's create this method. Def draw parenthesis self. And now we need to know the surface we're going to draw on. So we will pass it as an argument, comma screen, colon. Now we need the position of each occupied cell of the block in order to draw it on the screen. But we don't have this information yet, so we have to create it. To make our lives easier, let's create a new class named position. The position class will be helpful because it will allow us to represent a position in a two-dimensional grid using a single object. So we're going to create a new Python file named position.py. And now let's create the position class, which will have only two attributes, row and column. Class position colon. Def init parenthesis self colon. We need to pass in the row and the column in the constructor. So we type row, comma, column here. And now let's create the row and the column attributes. Self.row is equal to row and self.column is equal to column. Cool, the position class is ready and now we can represent a position on the grid with a single object. To simplify our code, we will use inheritance. We will create a separate class for each block which will contain the cell positions for each rotation state. These classes will inherit from the block class. Let's create a new file and let's name it blocks.py. Inside this file, we will create all the child classes, one for each block. First of all, let's import the two required classes. From block import block and from position import position. Now let's create a class for the L tetromino. Class L block parenthesis. As we said, this block must inherit the attributes and methods of the block class. So we have to declare that inside the parentheses. Block in here. Now the L block class is a child of the block class. Now let's create the init method. Def init parenthesis self colon. We need to initialize the block class. So we have to call the init method of the block class. We do this with this line of code. Super parenthesis dot init. The block constructor requires an ID. Let's give this block the ID 1, or for better readability, ID equals 1. Now all we have to do is to declare which cells are occupied. We are going to use the cells attribute of the block class. Self.cells is equal to curly brackets. As we said, the cells attribute is going to be a dictionary. The key of this dictionary will be the rotation state, a value from 0 to 3. So the dictionary is going to have 4 keys. Let's do it. 0, 1, 2, and 3. Now the value of each key will be a list containing the positions of the occupied cells. 4 cells for each block. Which cells are occupied when the L block is at the rotation state 0? Cells 0, 2, 1, 0, 1, 1, and 1, 2. Let's create a list with these cells using the position class. Brackets, position 0, 2, position 1, 0, position 1, 1, and position 1, 2. And lastly, a comma. That's it. The rotation state 0 is ready. Now we need to do the same thing for the other 3 rotation states. I will leave this as an exercise for you to practice. Based on the given graphic, please fill in the missing data. Take your time to work on it, and when you are ready, you can resume the video to see the solution. Welcome back! I hope you were able to successfully complete the exercise and that it helped you better understand what we are doing. So that's the complete class. I have filled in all the data for all the rotation states. We have to do the same for all the blocks. But before that, let's draw the first shape on the screen. Let's go back to the block class and work on the draw method. Now we have access to all the cells of the block for every rotation state. Check this out. Tiles is equal to self.cells brackets self.rotation state. This line retrieves the list of positions for the current rotation state of the tetromino as determined by the value of the self-rotation state attribute. Now for each cell we can draw a rectangle. We are going to use a for loop. For tile in tiles, Now we need to create a rectangle for each cell. For this we are going to use the pygame.rect method, so let's import pygame. Import pygame here. Now let's create the rectangle. Tile rect is equal to pygame.rect parenthesis. Tile.column times self.cellSize plus 1, comma, tile.row times self.cellSize plus 1, comma, self.cellSize minus 1, comma, self.cellSize minus 1. As we did in the grid class, we leave a 1 pixel offset when we draw the cells. Now it is time to draw the cell. Pygame.draw.rect parenthesis screen, comma, self.colors brackets self.id, comma, tile rect. That's it. The color value of the cell is obtained from the colors list using the block's ID as the index. Cool. Let's now use this method and see a block on the screen for the first time. Back to the main.py file. First, we have to import the block class. From blocks, import asterisk to import all the classes. Now let's remove the following lines of code from our main file since we use them for testing purposes only and they are not needed anymore in our final implementation. Now let's create an L block. Block is equal to L block parenthesis. Now in the game loop, let's draw this block by calling the draw method. Block.draw parenthesis screen. Let's run the game. The L block has appeared on the screen. How exciting! After all this code we have written, it's rewarding to finally see a block rendered on the screen. If you have made it this far, congratulations! You have accomplished the most challenging part, and things will start to progress more quickly from now on. Now we need to create classes for the remaining 6 blocks of the game. To do this, we will go back to the blocks class and create a separate class for each block, such as I block, J block, S block, etc. For each class, we will define the positions of the occupied cells for each rotation state and an ID from 1 to 7, similar to what we did for the L block. Once we have all the block classes defined, we can easily create instances of each block type in our main program. As an exercise, take a moment to write the remaining classes yourself. I will provide you with all the data you need for each block. Simply use the same format as we did with the L block class and fill in the positions of the occupied cells for each rotation state. Here comes the data. Pause the video for each block and fill in the data. Okay, as you can see, I have completed writing the code for all subclasses. I hope it was easy for you as well. The only tricky block is the O block, which has the same occupied cells for every rotation state, and we can simply use the same list for every rotation state. Or we can use just one rotation state now and deal with it later in the code. I'll choose this option. Let's only leave one rotation state in each dictionary. We are ready to test all the blocks. Let's go back to the main file and let's draw a T block. Let's change this line of code. Block is equal to T block. Now if we run the game, we can see the T block displayed. Cool. We can display all the blocks like this. Great job. We have completed step number 4. We have made a lot of progress. Now let's work on the next step. Let's write code to move the blocks on the screen. First of all, let's think about the problem. So far, we have created a game grid, and on top of that, we are displaying only the occupied positions of a smaller grid, the block grid. The origin for both grids is the top left corner. So, if we want to move the block, all we have to do is to move its origin point. For example, let's say the current position of the block is at the top left corner of the grid, which is at position 0, 0. If we want to move the block 3 columns to the right and 5 columns down, we just need two variables to hold the offset in the x and the y axis of the grid. Let's call these variables row offset and column offset. To move the block 3 columns to the right and 5 rows down, we will set column offset to 3 and row offset to 5. Then we will simply add these values to the row and column position of the block's origin point. So the new position of the block's origin will be 5, 3. This will move the block 3 columns to the right and 5 rows down the grid. Let's implement this in code. Let's go back to the block code. As mentioned earlier, we need to offset the positions of all cells in a block to move it. One way to do this is by adding two attributes to the block class. These attributes will hold the row and column offset of the block on the game grid. We can then update the position of each cell by adding the offset to its current position. Let's do it. Let's create two attributes. Let's call the first one row offset and set it to 0. Let's also create the second attribute and call it column offset and set it to 0 as well. Now let's create a method that will move the block by adding a row and a column offset to the cell. Def move parenthesis self, rows, columns, colon. We need to know how many rows and columns we have to move. Now all we have to do is to change the offset attributes. Self.rowOffset plus equals rows and self.columnOffset plus equals columns. Now we need to modify the positions of all the cells in the block according to the offset. To achieve this, we can create a new method in the block class which will calculate the actual position of each cell after the offset is applied. It's better to have a separate method for this rather than modifying the positions in the draw method, because we will need to recalculate these positions later to check for collisions. This way, we can avoid repetitive calculations. So let's create a new method called getCellPositions. Def getCellPositions parenthesis self colon. This method will return the positions of the occupied cells with the offset applied in a list. First, let's get the default cell positions for the current rotation state. Tiles is equal to self.cells brackets self.rotation state. Now let's create a new empty list to hold the moved tiles. Moved tiles is equal to brackets. Now we need to loop through all the tiles and add the offset to their positions. For position in tiles, colon. Position is equal to position with a capital P, that's a class, parenthesis, position.row plus self.row offset, comma, position.column plus self.column offset. And since we use the position class, we have to import it. So we type at the top of the file, from position, import position. Now back to the method. We just have to append the new position to the moved tiles list. Moved tiles dot append parenthesis position. And when the loop ends, we have to return the list. Return moved tiles. That's it, our method is ready. Let's use this method in the draw method to draw the block with the updated positions. We change this line here. Tiles is equal to self.getCellPositions. That's it. Let's test the game. Let's go to the main file. We have created a block. Let's move the block to the right 3 cells and to the bottom 4 cells. Block.move parenthesis 4,3. If we now run the game, we can see the block in its new position. Beautiful! We can now move the blocks of the game, but the blocks spawn at the top left corner of the grid. If we look at the online version of the Tetris game, the blocks spawn at the middle of the grid. Let's implement that. One easy way to do this is to alter the child class for each block. So we will move each block 3 cells to the right. We can do this inside the init method of each block. So in the blocks.py file, we alter all the init functions like this. Self.move parenthesis 0,3. I do the same for all the blocks one after another. Now let's go back to the main file, remove the move method call from here, and let's run the game again. As you can see, the block moved to its proper position. There are only 2 exceptions. The first one is the O block. If we create an O block, we can see it is not centered. We have to move it 1 cell to the right. So we go back to the O block class definition and we change the move call to 0,4. If we run the game once more, the O block is now centered correctly. The other exception is the I block. As you can see, if I create an I block, it is centered, but there is an empty row above it. We have to move it 1 cell to the top. So we go back to the I block class definition and we change the move call to -1,3. Now, if we run the game one more time, our I block is centered correctly. Beautiful. Moving on, we can now add input controls to move the block left and right. But before we dive into input controls, let's take a moment to organize our code for better management and maintainability. To improve code organization and make it easier to manage in the future, we will create a game class to hold the grid and block objects as well as various methods. The game class will serve as a container for all the elements of our game, such as the grid, the current and next block, and game state. It will also hold methods that manage the game's logic, such as updating the block's position, checking for collisions, etc. By centralizing all the game's functionality within this class, it will be easier to understand, maintain, and expand upon in the future. Additionally, it will also improve code readability and reduce the risk of bugs by keeping related code together in one place. Overall, creating a game class will greatly improve the organization and structure of our code base, making it easier to work with in the future. So let's create a new game class. We create a new file and we call it game.py. Now we type class game : def init parenthesis self : the game class must create and hold a grid. So let's import the grid class we have created. From grid import grid. Now we create a grid attribute. Self.grid is equal to grid. The next step is to create an attribute to hold the current block that is visible on the screen. But to do this, we have to select a random block from all the available blocks in the game. So let's first create a list of all the blocks. Self.blocks is equal to brackets. And now let's create all the blocks. I block, J block, L block, O block, S block, T block, and lastly, Z block. Of course, to use these classes, we have to import them. So at the top of the file, we type from blocks import asterisk, where asterisk means everything. Now we can create a method that returns a random block from this list. So we're going to need the random module. So let's import it as well. Import random. Now let's create the method. Def get random block parenthesis self and a colon. Instead of randomly selecting a block from the list every time we call the method, in the original game each of the 7 blocks appears at least once before reappearing. So we need to implement a way to cycle through the list of blocks, ensuring that each block appears at least once before repeating the cycle. So let's first select a random block from the list. Block is equal to random.choice parenthesis self.blocks. Now we need to remove it from the list, so the next time the method is called, this block will not be available. Self.blocks.remove parenthesis block. Now we can return that block. Return block. Lastly, at some point, the list will become empty, meaning no more blocks will be available. In that case, we can simply refill the list with all the blocks again. So before selecting a random block, we have to check if the list is empty. So we type if len parenthesis self.blocks equals 0 : then we create the original list. Let's copy this line from the init method. Our method is ready. We can now create the 2 attributes for the current and the next block. In the init method, we type self.currentBlock is equal to self.getRandomBlock and self.nextBlock is equal to self.getRandomBlock. Of course, the game class will also have a draw method which will be responsible for drawing all the objects on the screen. Def draw parenthesis self, screen, : we need to take the display surface to draw on as an argument. Self.grid.draw parenthesis screen and self.currentBlock.draw parenthesis screen. With this, the first version of the game class is ready. Now let's test it out. In the main.py file, we remove all the objects we created before and the calls to the draw methods of these objects in the game loop. Also, we remove these imports. We no longer need them. But we have to add another import. We need the game class now. So we type from game import game. We can now create a game object. Game is equal to game. And in the game loop we type game.draw parenthesis screen. That's it. If we now run the game once more, we can see it is working like before, but our code is more readable and easier to work with, as we are going to find out later. Let's move on to the next step of the game development, which is to make the player move the block. So let's add keyboard controls to the game. In order to control the movement of the block, we need to detect when the player presses certain keys on the keyboard. To do this, we add the following code inside the game loop. If event.type equals pygame.keydown : this line of code checks if the event type is equal to the keydown constant, which means the player has pressed a key. Now we need to determine which key the player pressed. We can do this by using the event.key attribute. This attribute returns a constant representing the key that was pressed. For example, to check if the player pressed the left arrow key, we can use this if statement. If event.key equals pygame.kLeft, this line of code checks if the event.key constant is equal to the pygame.kLeft constant, which represents the left arrow key. If the player presses the left arrow key, we have to move the block one cell to the left. We can achieve this by using the move method of the block class to move the block one column to the left. However, instead of calling the move method of the block directly, we will create a new method called moveLeft in the game class, as we want to encapsulate the game logic for handling the movement of the block. You are going to find out why in a minute. So let's go to the game class and create a new method called moveLeft. Def moveLeft parenthesis self colon. Now we just have to call the move method of the current block. Self.currentBlock.move parenthesis 0, -1. This way we move the block to the left. Now let's create another method for moving the block to the right. Def moveRight parenthesis self colon. Self.currentBlock.move parenthesis 0, 1. Lastly, let's create a method to move the block down. Def moveDown parenthesis self colon. Self.currentBlock.move 1, 0. Cool, let's now call these methods in the main file inside the game loop. If event.key equals pygame.kleft colon game.moveLeft, and then if event.key equals pygame.kwrite colon game.moveRight, if event.key equals pygame.kdown colon game.moveDown. Let's now run the game. It's beautiful to see our game in action, with the ability to move the block to the left, right and down. However, we have encountered a problem. The block is able to move outside of the game window from the left, right and bottom edges. We need to address this issue by implementing boundary checking to prevent the block from moving beyond the game window. The solution to this issue is straightforward. Since we know that the game grid contains 20 rows and 10 columns, we can simply check the current position of each tile of the block. If any of the tiles has moved outside of the game window, we need to move it back within the boundary of the game window. Let's implement this. First of all, let's open the grid class and add a new method in it. We are going to create a method that will check if a given tile position is inside the grid. Def is inside parenthesis self. We can pass in a row and a column, comma row, comma column. If row greater than or equal to 0 and row less than self.number of rows and column greater than or equal to 0 and column less than self.numCols, return true. Else return false. If the position, row and column, is inside the grid, we return true. Else, we return false. Now let's go to the game class and add a new method that will check if a block is inside the game window using the isInside method of the grid class we just created. Def block inside parenthesis self colon. First we need to get the list of all the tiles or cells of the block. Tiles is equal to self.currentBlock.getCellPositions. Now we need to check if any tile of the block is outside of the grid. For tile in tiles colon. If self.grid.isInside parenthesis tile.row, comma tile.column equals false colon. If the tile is outside of the grid, return false. Else, return true. Our method is ready. Now we can modify the moveLeft, moveRight and moveDown methods to check if after moving the block, it is still inside the game window. So inside the moveLeft method, we add the following code. if self.blockinside equals false, colon. If the block moves outside of the game window, we have to move it back in, so we undo the move. Self.currentBlock.move parentheses 0, 1. We do the same for the other two methods as well. If self.blockinside equals false, colon, self.currentBlock.move parentheses 0, -1. If self.blockinside equals false, colon, self.currentBlock.move -1, 0. Now we can go back to the main file and run the game once more. Perfect. The game works and the block cannot move outside of the game window. Keep up the good work. We are making steady progress towards completing our game. Let's remove step number 5 from the list. Moving on to the next step, which will take us just a few minutes. We now need to rotate the block. Luckily, since we have already entered all the data for each rotation state for each block, we don't have a lot of work to do to rotate a block. Let's go to the block class and create a rotate method for the block. Def rotate parentheses self, colon. Now we simply have to increase the rotation state by 1. Self.rotationState plus equals 1. We also need to check if the rotation state is equal to the number of rotation states the block has. Typically, blocks have 4 rotation states, except for the O block, which only has 1. If the rotation state reaches the maximum number of states for the block, we need to reset it back to 0. We can implement this by adding a conditional check after incrementing the rotation state. If self.rotationState equals len parentheses self.cells, colon. This approach applies to all blocks in the game, including the O block. Self.rotationState equals 0. Now we have to go to the game class and create a rotate method. Def rotate parentheses self, colon. Self.currentBlock.rotate. Now, in the main file, we will assign the action of pressing the up arrow key to rotating the block clockwise. In the game loop, where we check for key presses, we add the following. If event.key equals pygame.kup game.rotate. Let's run the game. Perfect, the game works. We can move the block and we can rotate the block each time we press the up arrow key. However, there is an issue with our code. When we rotate the block, it may end up in an invalid position where some of its cells are outside of the game window. This is something we need to prevent. Luckily, that's easy to fix. After rotating the block, we will check if the block is inside the game window. If it is not, we will undo the rotation. So first, let's create the undo rotation method in the block class. This method is similar to the rotate method. Def undo rotation parentheses self, colon. Self.rotationState minus equals 1. We just set the rotation state of the block to the previous one. The only thing we have to check is if the rotation state is 0. In that case, again, we will reset it. If self.rotationState equals 0, colon, self.rotationState is equal to len, parentheses, self.cells minus 1. Now we have to go to the game class and modify the rotate method to check if the block moves outside of the game window after rotating. If self.blockinside equals false, colon, then we have to undo the rotation. That's easy. Self.currentBlock.undo rotation. We are now ready to test the rotation in our game. Let's go to the main file and run the program once more. Beautiful. The game works and the rotation works and the block cannot rotate to an invalid position. The game won't let us. Perfect. One more step is now complete. Now, let's work on the collisions. First, we have to implement the automatic dropping of the block in a way similar to the Tetris game. To achieve this, we can call the moveDown method of the game class in the game loop. This will ensure that the block gradually moves downward on its own without any user input. So after the screen.fill call, let's add this line of code to see what happens. Game.moveDown. Now if we run the game, we can see that the block drops, but way fast. Why is this happening? The game loop is executed 60 times per second, so the game.moveDown method is called 60 times per second. This causes the block to move 60 cells to the bottom every second, which is why it moves so quickly. Instead of calling the game.moveDown method in every execution of the game loop, we need to update it at a slower rate, for example, every 200 milliseconds. This will slow down the block's movement and make it more visible on the screen. To achieve this, we are going to create a timer event using the Pygame library. First, let's create a custom event for our game and give it a name. GameUpdate is equal to pygame.userEvent in capitals. This line of code creates a variable called GameEvent and assign it the value of pygame.userEvent. UserEvent is a special event type in Pygame that can be used to create custom events. In this case, it is used to create an event that will be triggered every time the block's position needs to be updated. Now let's tell Pygame when to trigger this custom event. We want to trigger it every 200 milliseconds. To do this, we will use the setTimer function from pygame.time module. pygame.time.setTimer parenthesis GameUpdate, 200. This function creates a timer that will trigger the GameUpdate event every 200 milliseconds. The first argument is the event that needs to be triggered, and the second argument is the interval in milliseconds. In this way, we are ensuring that the game is updating the position of the block every 200 milliseconds and not 60 times per second, avoiding the problem of the block moving too fast. Now, in the game loop, as we said before, we check for any events that happened since the last time the game loop was executed. Let's add a check for our custom event. This is very simple. If event.type equals GameUpdate, game.moveDown. This code checks if the event type is equal to the GameUpdate, and if it is, it calls the moveDown method of the game object. This ensures that the block's position is updated only when the GameUpdate event is triggered and not every time the game loop is executed. It is important to remove the call to the game.moveDown method that was previously in the game loop to avoid updating the snake's position more than once per interval. With this setup, let's run the game once more to see if the changes have taken effect. As you can see, the block is moving at a slower pace, which is exactly what we want. However, we now face another issue. When the block reaches the bottom of the screen, it doesn't lock in place, and we can still move it right and left. This is not the desired behavior. Let's address this problem. To fix this issue, we need to implement the locking mechanism for the block when it reaches the bottom of the game window. This will ensure that the block locks in place and becomes immovable once it reaches the bottom. In other words, we have to change the grid values to hold the position of the block when it reaches the bottom of the window. So in the game class, in the moveDown method, we check if, when moving down the block, it gets out of the game window. In that case, we undo the move. This is when we must lock the block in place. Let's call the lockBlock method, which we will create at once. self.lockBlock. Now we are going to create this method. Def lockBlock parenthesis self colon. In this method, we need to update the game grid values to represent the location of each cell of the block on the grid at the time it touches the bottom of the screen. For each cell, we will store the ID of the block in the corresponding cell on the game grid. The ID value also corresponds to the block's color. This will mark the cells as locked and indicate that the block has reached its final position at the bottom of the game window. First, let's get the current positions of all the tiles of the block. Tiles is equal to self.currentBlock.getCellPositions. Now, for each cell position, we will store the ID of the block in the grid. For position in tiles, self.grid.grid brackets position.row brackets position.column equals to self.currentBlock.id. Now we need to spawn a new block on the screen. We already know which is the next block. It is saved in the next block attribute. So we type self.currentBlock is equal to self.nextBlock. And we have to update the nextBlock attribute with another random block. Self.nextBlock is equal to self.getRandomBlock. Let's go back to the main file and test the game once more. Now, each time a block reaches the bottom of the screen, it locks in place and a new block is spawned. The newly spawned block cannot collide with the blocks that are already locked in place. We need to fix this problem. The solution to this is again very easy. When we move the block one row to the bottom, we need to check if the cells of the grid the block occupies are empty or not. If they are not empty, we have to undo the move and lock the block in place on the grid. So let's create a method that will check if a cell of the grid is empty or not. While we can implement this method in either the game or the grid class, it makes more sense to write it in the grid class as it logically belongs there. In the grid class, we create the method def is empty parenthesis self, row, column, colon. If the cell contains the value 0, if self.grid brackets row brackets column equals 0, colon, return true, else return false. Great. In the game class now, let's create a method that will check every cell of the block to see if it is on top of an empty cell of the grid or not. Def block fits parenthesis self, colon. Again, we get all the cells of the block. Tiles equals to self.currentBlock.getCellPositions. For tile in tiles, now we have to check if any of the cells is occupied. If self.grid.isEmpty, parenthesis, tile.row, tile.column equals false, colon, in that case, we have to return false. Else, if all the cells are empty, we return true. The block can move to the specified position. The last step is to modify the move down method. We need to check if the block after moving one row down is inside the game window or if the block fits in its new position. So we add this, or self.blockFits equals false. Now, if we attempt to move the block down and encounter a cell that is already occupied, we undo the move and lock the block in place. Let's try it in the main file. The game runs, and as you can see, when a block collides with another block, it locks in place. It no longer overrides it. That's very cool. Again, we have a small problem to fix though. We check if a block collides with another block only when we move the block down. Now, when we move it left or right, or if we rotate the block, this results in a similar problem as you can see. We have to fix it. Since we now have the function needed to check if a block fits in its new position, the fix to that problem is very easy. In the game class, in the moveLeft method, we have to add the following check, or self.blockFits equals false. We need to check if the block after moving one column to the left is inside the game window or if the block fits in its new position. If this is false, we undo the move. It is not a valid move. We do the same thing to the moveRight method. Or self.blockFits equals false, and with the rotate method as well. Or self.blockFits equals false here. And that's it. Let's test the game once more. Good job! The game works as expected, and the blocks can only move to valid positions. We can no longer overwrite the blocks that already exist on the grid. Another step is now complete. The game logic is almost ready. The next step is to check for completed rows. All we have to do is to check if a row is full, and when it is, we have to clear it and move all the occupied cells above that row one row down. This is how we are going to do it. We will scan every row of the grid from the bottom to the top. We are going to need a variable to hold the number of completed rows. If we find a completed row, we will increase the completed variable by 1. Then we will clear the row and check the next row. If it is not completed, we will move the row down by the value the completed variable contains. This procedure works for any number of completed rows. See what happens if we find 2 completed rows. We check the first row, it is completed, so we increase the completed variable by 1 and we clear the row. Then we check the next row, it is completed, so we increase the completed variable by 1. It is now 2 and we clear the row. Next we check the next row, it is not completed, so we have to move this row down by exactly 2 rows. And with the same procedure, we check every row of the grid. Now that we know what we have to do, let's implement this in code. We need to write some methods in the grid class. First, we need to write a method to check if a row is full. Def isRowFull, parenthesis, self, row. We are going to give this method a row as an argument. Now, all we have to do is to check if any of the cells in a row are empty, which means they have a value of 0. If any cell is empty, then the row is not considered full. We need to get every column of the grid. For column in range, parenthesis, self.number of columns, colon. Now we need to check if the value of the cell is 0. If self.grid brackets row brackets column equals 0, colon. If it is 0, we have to return false. Return false. Else, we return true. Return true. Now we need to create a method that will clear a row. In other words, it will set the value of each cell of that row to 0. Again, this method is very easy. Def clear row, parenthesis, self, row. Again, we need the row as an argument. For column in range, parenthesis, self.nabCols, colon. Again, we get all the columns. Self.grid brackets row brackets column is equal to 0. And we set the value of each cell of that row to 0. Our method is ready. Now we need yet another method to move a row down by a specific number of rows. Def move row down, parenthesis, self, row, number of rows. Here we need 2 arguments, the row to move down and how many rows to move down. Again, we need to get all the columns. For column in range, parenthesis, self.number of calls. Now we need to change the values of the destination row to be equal to the current row. Self.grid brackets row plus number of rows brackets column is equal to self.grid brackets row brackets column. Lastly, we have to clear the current row. Self.grid brackets row brackets column is equal to 0. In summary, this code moves a row in the grid down by number of rows by copying the values from the original row to the new row and clearing the original row. We are now ready to create the method that will combine all these methods. Def clear full rows, parenthesis, self, colon. This method will check all the rows from the bottom to the top to see if any row is completed. So we need a completed variable. Completed is equal to 0. Now we need to check every row starting from the row 19 to moving down to row 0. For row in range, parenthesis, self.numRows -1, 0, -1, colon. This for loop iterates through the rows of the grid in reverse order, starting from the last row and going up to the first row, row 0, with a step of -1 to move upward. Now we have to check if the current row is full using the isRowFull method we wrote earlier. If self.isRowFull parenthesis row colon. If the row is full, we have to call the clearRow method to clear all the cells in the current row. Self.clearRow parenthesis row. Then we have to increment the completed counter by 1 to keep track of the number of rows completed. Completed plus equals 1. Now, if the current row is not full, but some rows have already been cleared, it means that we have to move that row down. Elif completed greater than 0, colon, self.moveRow down, parenthesis, row, comma, completed. Lastly, let's return the completed rows. We will need them to calculate the score later on. Return completed. Great! Now we are ready to use that newly created function in our game. We have to go to the game class, and in the lockBlock method we have to call the clearFullRows method. Self.grid.clearFullRows here. Let's navigate back to the main file and run the game once more. Now, each time we complete a row, it should disappear from the grid. Okay, let me place some blocks on the grid. Here we go. A completed row. It goes away. Perfect. Another very important step of the game is now complete. Let's now work on the next step, which is to make the game end. The game ends when a newly spawned block overlaps with a block that is already locked in place on the grid, preventing further movement or placement of the new block. In our game, the new block is spawned at the top of the screen, similar to the online version of Tetris. However, in some other versions of Tetris, the new block is spawned outside of the visible screen and then gradually slides into the play area, one row at a time. So, to check if the game has to end, all we have to do is to check if the newly created block fits in the grid. If it does not fit, the game is over. So, let's call this behavior in the game class. That's easy. When we lock a block in the grid, we create a new block. Now we have to check if that new block fits in the grid. If self.blockFits equals false. If the block does not fit, we have to end the game. Let's create a GameOver attribute to the game class and set it to false. At the init method we type self.GameOver equals false. Now we need to set this attribute to true when the game ends. So in the lockBlock method, if the block does not fit, we set the GameOver attribute to true. The last thing we have to do is to stop the game from updating every 200 milliseconds if the game is over, and don't let the user move the block if the game is over. So in the main file we add this check here. And game.GameOver equals false, which means the game will only update if it is not over. We do the same thing with the movement and rotation of the blocks. Here, here, and here. Perfect, let's run the game with the new functionality with an increased game speed to check for the game over condition. As you can see, when the new block spawns on top of an occupied cell, the game immediately ends, and the player is no longer able to move the block. But so far there is no way to restart the game after it is over. That's what we're going to work on now. Let's modify the main file to restart the game whenever a key on the keyboard is pressed. In the game loop, where we check for key presses, we have to add this check. If game.GameOver equals true, the game is over and a key is pressed. We need to restart the game, so we have to set the GameOver attribute to false. Game.GameOver equals false. And we have to reset the game. Let's call a reset method, game.reset. We haven't created a reset method in the game class yet, so let's create it now. In the game class, we type def reset parenthesis self colon. What do we need to do? We have to clear the grid, self.grid.reset. But we don't have a reset method for the grid class. Let's create one. We go to the grid class and we create a new method, def reset parenthesis self colon. Now we need to loop through all the cells and set their value to 0. For row in range, parenthesis, self.number of rows, colon. For column in range, parenthesis, self.numCols, self.grid, brackets row, brackets column equals 0. Okay, the grid is now reset. Let's now go back to the game class. What do we have to do when the game ends? We need to select a new random current block from the list of blocks and a new next block. But first, we have to create a new list with all the blocks. Again, we copy this line of code, which creates a list of all the blocks from the init method, and we paste it here. And then we select a random block to be the current block and another one to be the next block. Self.currentBlock is equal to self.getRandomBlock and self.nextBlock equals to self.getRandomBlock. Let's run the game one more time. Let me drop some blocks quickly to see what happens. Perfect. As you can see, the game is now over and it waits for a key press. If I press any key on the keyboard, the game starts over with a clear grid. Very cool. Congratulations, you have successfully implemented the game logic. Well done on reaching to this point. Another step is now complete. Let's now work on the next step. Let's add a user interface to the game to look like this. The user interface consists of several components. A background that serves as the canvas on which all the game elements are drawn, a title text element for displaying the score text, a rounded rectangle to display the score value, a text element for rendering the actual score value, a title text element for displaying the upcoming shape, next shape, a rounded rectangle to display the next shape, the actual next block shape itself, and a title text element for displaying the game over message. These elements work together to create the visual interface for the game, providing information on the score, the next shape, and the game over condition. Let's start by creating the background. First, let's make the game update slower once again by changing this value to 200. Now, the following line of code creates the display surface, which serves as the canvas on which we draw all the game elements. The game window is sized to match the dimensions of the grid. Let's give the grid an offset of 10 pixels to the left, top and bottom, and 200 pixels to the right. The new dimensions of the display surface will be 500, 620. If we run the game now, we can see that the grid is drawn from the top left corner of the game window without any offset. Let's give it a 10 pixel offset to align it properly. To properly align the grid within the game window, we need to make a change in the draw method of the grid class. We can adjust the x and y coordinates of the rectangle being drawn by adding 10 pixels to both. So we can update the expression 1 plus to 11 plus in order to achieve the desired offset. Similarly, we need to update the draw method of the block class to add 10 pixels to the x and y coordinates of the cell being drawn. This can be achieved by modifying this line to look like this, plus 11 here and here. Cool, let's run the game one more time. Perfect, as you can see, the background of the game is now visible. Now, moving on to the next UI element, we need to print the text score on the screen. In Pygame, to create and display some text, we need to follow 3 steps. First, we need to create a font, then a surface with the text we want to display, and then we can display that surface using the bleed method of the display surface object. First, let's draw the score title. So, outside of the game loop, below the pygame.init call, let's create a font and call it title font. Title font is equal to pygame.font.font, and we have to give it a font family and a size. For the font family, I will enter none, so it will use the default font of the Pygame module. For the size of the font, I give it the value 40. The first step is done. Now we have to create a surface for the title. To do this, we use the render method from our title font object. Score surface is equal to title font.render parentheses. We pass in the string that we want to display, quotes, score. We set the anti-alias argument to true and finally we set the color of the font. I am going to set it to white. White is a tuple with the values 255, 255 and 255. So let's store this value in the color class as well. So we open the colors class and we add the white color definition as well. Also, now that we work on the color class, let's add the dark blue color definition for the game background as well. We cut it from the main file and we paste it in the colors class. Lastly, I'm going to add another color that we're going to need in a minute. Light blue is equal to 59,85,162. Now back to the main file. We have to import the colors class. From colors, import colors. Then in the game loop here, we have to change this line like this. Colors.darkblue. And inside the render call we were working on, we add the following. Colors.white. This way it is more readable and we define all the colors in just one place. Now we can call the bleed method to display the score surface on the display surface, which we have named screen. Bleed means block image transfer. Most of the time in Pygame we are going to be bleeding images to the display surface. We will call the bleed method inside the game loop. We have to pass in the surface that we want to display and the location on the screen. So we type screen.bleed parenthesis score surface and the position we want it to be in a tuple. Let's say parenthesis 365,20,50,50. Let's run the game. Cool, the score title appeared in its position. Now let's add a rounded rectangle of light blue color to draw the score on. To draw a rectangle, we first need to create a rectangle object. Let's create it here, outside of the game loop. Score rect is equal to pygame.rect. We need the x and y coordinate of its top left corner. Let's enter 320,55 for the x and the y, and we need the width and the height of the rectangle. Let's enter 170,60. The rectangle is ready. Let's print it on the screen. In the game loop, we are going to call the pygame.draw.rect method. Pygame.draw.rect parenthesis screen. Now we need a light blue color, so colors.lightblue. Now we need the score rect, score rect, and now we type 0, 10 to make the rectangle have rounded corners. If we run the game now, we can see that a new rounded rectangle appears on the screen. Perfect. With the same procedure, we're going to create the title next and the rounded rectangle below it. Again, outside of the game loop, we create a surface for the title next, using the same font, the title font. We can reuse the same font because we want all the titles to be identical in font family and font size. So we type next surface is equal to title font dot render parenthesis quotes next true colors dot white. And now we have to display that surface with the bleed method inside the game loop. Screen.bleed parenthesis next surface parenthesis, and now we need a tuple with the position on the screen. We will enter these values 375, 180, 50, 50. Upon running the game again, you'll now see the newly added title text on the screen, which is a great addition to the user interface. The next step is to draw a rectangle below the title next to display the next shape. Again, we're going to create a rectangle. Let's name it next rectangle. Next rectangle is equal to pygame.rect parenthesis 320, 215, 170, 180. And now we can display it on the screen. So in the game loop, we type pygame.draw.rect parenthesis screen, colors.lightblue, next rect, 0, 10. Perfect. If we run the game, we can see the new rectangle displayed. Now, the last thing we have to do is to display a game over message when the game is over and the basic UI elements will be ready. Again, we are going to use the same font. So, outside of the game loop, we are going to create a new surface like this. Game over surface is equal to title font dot render parenthesis quotes game over comma true comma colors dot white. And now in the game loop we have to display it. Screen dot bleed parenthesis game over surface comma parenthesis 320 comma 450 comma 50 comma 50. Let's see if this works, and then we will update our code to display this text only if the game is over. Beautiful, the game over message appears on the screen. We can implement a simple check in the game loop just before drawing the game over message to ensure that the message is only shown when the game is actually over. If game.gameover equals true, and then we have to indent this line to belong to the if statement. That's it. Let's test our game. Beautiful. The game works fine and the game over message does not appear unless the game is actually over. When we press any key, the game restarts and the message disappears. With that, another step is now complete. Well done. We are now very close to completing the game. Keep up the good work. The next step is to add scoring to the game and display it on the screen. However, it is important to note that our version of the game is a simplified version of Tetris and does not include all the features of the original game for the sake of simplicity. Therefore, the scoring system will also be limited in our implementation. In our simplified version of Tetris, the player will earn points for clearing lines and moving the block down. Specifically, we can assign the following point values to different actions. 100 points for a single line clear, 300 points for a double line clear, 500 points for a triple line clear, and 1 point for each block moved down by the player. To implement this scoring system, we will need to add a score attribute to our game class. So, in the game class, in the init method, we add self.score equals 0. Now, let's create a method that will be responsible for updating the score of the game. Def update score. We need to know two things: the number of lines cleared and the number of times the player moved a block down. So we need two arguments. Parentheses. Self, comma, lines cleared, comma, move down points. Now we need an if statement to award points according to how many lines the player has cleared. If lines cleared equals 1, colon, self.score plus equals 100. Else if lines cleared equals 2, self.score plus equals 300. Elif lines cleared equals 3, colon, self.score plus equals 500. Lastly, we need to add 1 point each time the player moves the block down. Self.score plus equals move down points. That's it, our method is ready. Let's call it. The first place where we need to call it is inside the lockBlock method, where we clear the rows using the clearFullRows method of the grid class. This method returns the number of rows cleared, so we can save this information in a variable. Let's call it rows cleared. Now we need to call the updateScore method and pass in this variable as an argument. Self.updateScore, parentheses, rows cleared, 0. Now we need to increase the score when the player moves the block down. We have to do this in the main file. But before we leave this file, let's reset the score to 0 when we reset the game. In the reset method, we type self.score equals 0. In the main file now, in the game loop, where we check for user input, we have to call the updateScore method when the user presses the down key. Game.updateScore, parentheses, 0, 1. That's it. Now we need to display the text on the screen. We will use the same font object we used for the other text we displayed on the screen. Again, we will create a surface for the score, but this time we will create the surface for the score inside the game loop. Can you think of a reason why? Take a moment to consider it. I'll wait. The score is dynamic and changes throughout the game as the player clears lines and moves the block. That's why we need to create a new surface for the score each time we want to update and display it on the screen. It is not a static text, so inside the game loop we create the score surface like this. Score value surface is equal to titleFont.render parenthesis str parenthesis game.score, true, colors.white. The score is an integer, so we need to convert it to a string before displaying it. That's why we call the str method here. Now, let's display that surface on top of the score rect. So we type this after the line that draws the score rect on the screen. Screen.blit parenthesis score value surface, comma. Now we need to define the position on the screen where we want to draw the text. This is tricky because the score is not static, its size will change. If we want it to be centered, we can use a small trick. Check this out. Score value surface dot get rect parenthesis center x is equal to score rect dot center x, comma center y is equal to score rect dot center y. This code calculates the rectangle that encloses the score value surface text and centers it on the score rect horizontally and vertically so that the score is displayed in the middle of the score rect. Perfect. Let's run the game. Amazing stuff. The score is now displayed on the screen. Each time I move the block down, the score increases. Let me show what happens if I complete a row. Give me a second to achieve it. The score increased by 100 points. Beautiful. Our scoring system works. Another step is now complete. We are now just 2 steps away from completing our Tetris game. The next step is to draw the next block on the screen. This step is easy to implement thanks to the use of object-oriented programming principle in our game design. We will work on the block class. We already have a draw method that draws a block on the screen. We will reuse the same draw method. We need to draw the block but at another position, so we need an offset. So we will add 2 arguments to the method, an offset x and an offset y argument. Now, in this line where we create the rectangle to draw on the screen, we need to add offset x plus here and offset y plus here, and we can remove the plus 11 from here and here since we now have arguments for the offset. The draw method is ready. Let's now go to the game class. In the draw method, we draw the current block. We need to modify the method to add the offset x and offset y values. We add comma 11 here. It is the hard-coded offset we removed from the draw method. Now, all we have to do is to draw the next block on the screen. Self.nextBlock.draw parenthesis screen, comma, and let's enter 270, 270. Let's run the game. Beautiful. As you can see, the next block appeared on top of the next rectangle. Cool. You can see that the block changes each time I place a block on the grid. But there is something that bothers me. The I block and the O block are not centered in the rectangle. I have to fix it. So let's go back to the game class. In the draw method, we have to check the ID of the next block before it is drawn on the screen. If self.nextBlock.id equals 3, that's the I block, give this block its own offset values. Self.nextBlock.draw parenthesis screen, comma, 255, 290. Elif self.nextBlock.id equals 4, that's the O block, self.nextBlock.draw parenthesis screen, comma, 255, 280. Else, all the other blocks work okay with the default offset. Self.nextBlock.draw parenthesis screen, comma, 270, 270. It is not the most elegant solution, but it works. Great job. Running the game again, we can now see that the blocks are appearing centered on the rectangle. This is a significant progress and another step towards completing our game. Now let's add sounds to the game. Sounds are important to a game as they provide feedback, create atmosphere, evoke emotions, and contribute to the identity of the game. Due to copyright reasons, I won't be using the original Tetris soundtrack for the game. Instead, I'll be using a theme created by my friend Spiros specifically for this video. The sound files are included in the GitHub repository of the game. You can find more amazing music by Spiros in a link provided in the video description. Now in my game folder, I have created a new folder named Sounds and placed 3 sound files in it. One is named music.og, which contains the background music for our game, and the other 2 are rotate.og and clear.og, which contain sound effects for rotation and clearing rows respectively. Pygame supports various sound file formats, including MP3s, but due to some known issues with MP3 support, I opted to use the OGG format. Firstly, we need to start playing the background music when the game starts and ensure that the music loops continuously as long as the player is actively playing the game. We can do this either in the main file or in the game class. Let's implement it in the game class. First, we need to import the Pygame module in this class since we haven't done so yet. Import Pygame. Now we have to load the music. In the init function of the game class, we add this line of code. pygame.mixer.music.load parentheses. And now we have to add the file we want to load in quotes. Quotes sounds/music.og. The next step is to play the music. We have to use this line of code. pygame.mixer.music.play -1. This line of code plays the background music with the argument -1, indicating that the music should loop indefinitely. Let's test it. Perfect! We can hear the music of the game. Now, all we have to do is to add sounds for rotating and for clearing a row. We go back to the game class and we add 2 attributes in the init method. Let's name the first one rotate sound. Self.rotateSound equals 2. Now we have to load the sound. Pygame.mixer.sound parentheses. And now we have to enter the file name in quotes. Quotes sounds/rotate.og. We do the same thing for the clear sound. Self.clearSound equals 2. Pygame.mixer.sound parentheses quotes sounds/clear.og. All the sounds are now loaded and ready to play. All we have to do now is to call the play method of each sound when we need to. Let's work on the rotate sound first. We need to play the sound when we rotate the block. So in the rotate method of the game class, we have to add a call to the play method. Here we check if the rotation is not valid. If the rotation is valid, we need to play a sound. So we add else self.rotateSound.play. Cool! We now have to play the clear sound when we clear some rows. In the lockBlock method, we call the clear full rows method, which returns the number of rows cleared. If the number is greater than 0, we have to play the clear sound. So let's add a check. If rows cleared greater than 0, self.clearSound.play. We can also add the updateScore method inside the if statement now that we have that check in place. The player will be awarded points only if it has cleared a row, so we don't need to call this method every time the user places a block on the grid. Believe it or not, with this change, our game is ready. Let's test it out. Our game is ready. The music is playing, the sounds are playing, the score is updating, and in general, the game works as expected. Congratulations on finishing the Tetris tutorial. You worked really hard and learned a lot about making games. By creating this classic game, you improved your skills and gained valuable experience that will help you in your future projects. Be proud of yourself and keep up the good work. To further your knowledge and continue learning, be sure to subscribe to our channel for more tutorials like this one. We will keep you updated with new and exciting projects that you can work on to enhance your skills. Thank you very much for watching this video. I'll see you in the next one.